We often view the Earth as a static, two-dimensional map. In reality, we are living inside a massive thermodynamic engine. The machinery starts miles above our heads, where millions of tons of atmospheric gas crush down in distinct layers of pressure, stacking all the way up to the exosphere. Dive 100 miles below the crust, and you hit the asthenosphere. The asthenosphere is a semi-fluid layer of the upper mantle, where extreme radioactive heat boils rock into a churning plastic state. Here, convection currents of magma rise and fall, acting as the primary furnace for the planet's internal machinery. As these liquid rock currents circulate, they scrape against the solid underside of the Earth's crust. This immense heat and friction physically drags pieces of the outer shell, the tectonic plates, across the globe at about the speed that human fingernails grow. Where these massive plates crash into each other or dive underneath one another, the crust fractures. Around the edges of the Pacific Plate, this continuous collision creates a 25,000-mile horseshoe of active volcanoes and seismic fault lines. When denser ocean plates are dragged down into the mantle, a geological process known as subduction, the melting rock violently erupts back to the surface. Further west, a different type of collision is playing out. The Indian tectonic plate is actively slamming into the Eurasian plate at a rate of about 2 inches per year, forcing the solid landmass to buckle and fold upward. This grinding, underground heat engine dictates the topography of the surface. The resulting mountains, valleys, and fault lines form the physical stage where human history actually takes place. That ongoing collision between the Indian and Eurasian plates buckled the Earth's crust so severely that it raised the Himalayas. This wall of rock reaches over 5 miles into the sky. At that extreme altitude, the temperature drops, trapping atmospheric moisture as massive glaciers. When these ice reserves slowly melt, they feed billions of gallons of continuous, year-round water into river systems like the Ganga and the Brahmaputra. This map shows the path of the Brahmaputra River. Flowing eastward across the Tibetan Plateau, the river hits the Namcha Barwa mountain and executes a massive U-bend, dropping 2,000 meters in elevation as it violently carves its way down into India. Unlike the permanent ice-fed rivers of the Himalayas, the waterways in southern India, like the Mahi and Indrayani, lack a glacial source. Instead, they rely almost entirely on seasonal rainfall from the monsoon to keep their riverbeds from running dry. The shifting tectonic plates might dig the physical trenches and raise the mountains, but the rock alone cannot sustain life. The invisible currents of the atmosphere ultimately decide which of these geographical basins fill with water and which are left as dust. The atmosphere has its own immense circulation system, driven by the sun. Intense solar radiation at the equator heats the air, causing it to rise rapidly. This warm air travels towards the poles at an altitude of 10 to 15 kilometers, cools down, and sinks back to the surface near the 25-degree latitudes, creating a continuous looping cycle known as a Hadley cell. Because the Earth is spinning, this falling air does not travel in a straight line. The planet's rotation deflects these massive wind currents to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection of moving air across a rotating body is called the Coriolis effect. These precise global wind belts gather moisture from the warming Indian Ocean and physically drive it toward the landmasses. During the summer, this mechanism powers the southwest monsoon, dumping the vast majority of the Indian subcontinent's annual rainfall in a matter of months. This system is highly sensitive to temperature shifts in the ocean. When Pacific waters warm during an El Niño event, it alters the air pressure gradients and weakens the monsoon rains over India. Conversely, the Madden-Julian oscillation, a moving band of wind and rain that circles the equator every 30 to 60 days, can temporarily intensify these downpours as it passes over the region. Without these high-altitude wind belts consistently dragging ocean moisture over the continents, the massive agricultural economies of South Asia would collapse. The atmospheric engine is the delivery mechanism for the fresh water that billions of people drink. This combination of rock and wind also dictates where the global economy is most vulnerable. A massive percentage of modern maritime trade is forced to navigate through a very specific oceanic bottleneck, the Red Sea. The Red Sea exists for a very specific structural reason: the African and Arabian tectonic plates are actively tearing away from each other, allowing ocean water to flood into the expanding rift. At its southern tip, this tectonic split narrows into the Bab el-Mandeb Strait. Today, this tight geological corridor is packed with commercial shipping lanes and the undersea fiber optic cables that carry Europe and Asia's internet traffic, making it a highly exposed target during regional military conflicts. Thousands of miles away, the South China Sea presents another geographical flashpoint. Over millions of years, ancient geological epochs compressed organic material beneath the seabed here, creating an estimated 11 billion barrels of oil and 190 trillion cubic feet of natural gas. This map illustrates the resulting geopolitical friction. Because of the extreme concentration of physical resources, complex human disputes are projected directly onto the water. The red 9-dash line shows how China's historical claims heavily overlap neighboring exclusive economic zones. We often assume that modern engineering and aviation have untethered us from the constraints of the natural world. Yet the most advanced military fleets and the trillion-dollar global supply chain remain physically funneled through the exact geographic corridors carved by tectonic shifts and dictated by wind patterns. The borders we draw on paper do not govern the flow of water, the creation of petroleum, or the friction of the continental plates. The ancient fault lines and atmospheric pressure systems hold the actual authority over where cities can thrive and where ships can sail. A moment of wonder. When you view the planet as a complete, functioning thermodynamic system, the scale of our infrastructure shrinks. Human civilization, with all its economies, laws, and conflicts, is not the master of the Earth. It is simply a fragile, temporary layer resting quietly on the surface of an ancient, indifferent planetary machine.